So, shall I begin? Yeah. So today I'd like to introduce inequality. Of Noether type. This is a threefold version, so dimension. Three. So this. So the problem is parallel to surface case. So if we, as we know that if S is a minimal surface, of general type, then the Noether's inequality says that Ks squared, this is 2pg minus 4. Or in an equivalent way, this is 2, so let's say Ks squared 2 chi of Os minus 6. Okay, so so on the surface case, these are almost equivalent, but in threefold case, that's for minimal threefold. Usually, so if you have a threefold x, which is minimal, normally chi of Ox is only integer. It can be either positive or negative or 0. So if you want to find some inequality, some linear inequality, then it's hard to put chi Ox in the inequality. So it's natural we try only consider something the geometric genus. So the history of this topic is as follows. First, it was studied by in 1990, maybe in 1992. 92, and Masanori, Kobayashi. He first started this kind of question, and he proved that. He proved two results. The first result is that if the canonical map is generic finite, I should put a closure here. Then there is kx cubed is greater than or equal to pg of x minus 6. So this is for arbitrary minimal threefold. Another more important contribution is that he construct the following examples. There exists canonically polarized threefold. Here, canonically polarized means smooth and kx ample. Threefolds. Say xk. Here, k can be arbitrary integer, positive integer, satisfying the following. So pg of xk is so this is this is 3k plus 4, and the volume kx cubed. This is 4k plus 2. Okay, so this is an infinite family, and therefore you see that there is equality. So kx cubed, this pgx minus over 3. So this is a very interesting example. So this tells us that if you want to generalize this Noether's inequality to high dimensions, it's not as what you can you can conceive or you can guess something. A very naive expectation is 2pgx minus 2n. N is the dimension of this variety. So this inequality cannot hold. So so therefore, we want to study this this problem. Okay. So the best you can guess is that whether maybe for any threefold. So our guess is that maybe for any minimal threefold, maybe this over 3 pgx minus, maybe this holds. I mean, this is only a guess. It's not verified yet. But today I will show you the evidence, and in special case, this is 0. Okay, so let me put this as let me put this inequality some label. Say this is inequality star to give convenience to my lecture. So and then in 2004, I verified this inequality for so I verified this inequality. Say this holds for or canonically polarized threefold. Sorry. And then 2 years later, this was generalized to smooth minimal case by Catanese, myself, and Deqi Zhang. So this holds for X smooth minimal. Okay, and actually, so the open problem is, we felt that in this paper we conjectured that this inequality holds for Gorenstein minimal threefold. So the last year, Meng Chen and myself. So we verified this for Gorenstein minimum. Threefolds. Of course, our objects are general type. Okay. So, so this is so far what we know. But so today, so in this lecture, I will show you actually this inequality holds in many, in most cases, and I can prove, I give a very concise proof, and I tend to prove for all of arbitrary threefolds. Of course, so far, no counterexample to conflict with this inequality. So this is what we hope this is true for all minimal threefolds. So the main tool is from the technique I explained yesterday. So the key theorem, most of the cases we will use the key theorem to,
So you put some limitation on the singularities, or just
so arbitrary means minimal, in high dimension minimal means Q factorial terminus, right? Yes. So so from now, the example is they construct a double covering from rank 2 vector bundle over P1. And in Kobayashi construction, that's by double covering. It has a 1-2 surface vibration onto P1. So first, I should say that this is so this is verified for PG. So I think this is a special case. It's contained in my previous papers, so I omit this. So anyway, from now on, we can always assume that my premises is that X is a minimal threefold of general type with PG at least 5. Actually, if this doesn't hold, then it's, you can see that PG should be larger. For example, since this is a rational number, this positive rational number, then kx cubed smaller than 4/3 PG x minus 10/3. Okay, so this is positive. So this means that PGX is larger than 5/2. Okay, so PG at least 3. But in 3 and 4 cases, it's yeah. In my previous estimates, it's I can verify that this always holds. So I assume that PG is large. So therefore, the canonical map is non-trivial. It's not 0. Non-trivial. So therefore, I can use the technique I explained yesterday, the key theorem. So let me recall you. So I have so in the case is so in this case we set m naught is 1, and we have pi up star of kx, and I set I take the linear system lambda to be kx in my setting yesterday. So I have a moving linear system. So kx prime. So this is moving part plus fixed part. So I take a general, irreducible, generic irreducible element S. So S is a generic irreducible element. Of this linear system M. So by my assumption, this is base point free after blowing up. So X prime is a smooth model. Okay, I always have this this diagram X prime. So X then I take Stein factorization. I have induced vibration F from X prime onto gamma. So so it's not difficult to verify this, because this is already proved by Kobayashi. So I only care about the fiber case. That is, the dimension of gamma is either 1 or 2 in both cases. So recall that pi up star kx is something like theta s plus e prime. Well, e prime is positive, is effective Q divisor. Okay, so for example, if I study the first case, the case 1. Case 1, dimension of gamma equals to 2. Okay, this is dimension is 2. So I take C to be a general fiber of F. So therefore, the genus of C is at least 2. Okay. So yeah, in this case, we know that S restrict to S. So this is equivalent to a number beta C. Well, beta is at least PG of X minus 2. Okay. So I from here I have I have this relation pi up star of kx when I take the restriction. So this is beta c plus e prime restrict to s. So I times this by pi up star kx s. So this is left and big. So then I get Yeah. Sorry? Sorry. Yeah, I already. Yes. This is. No. Theta equals. Yeah, theta is 1 in this case. Sorry. In this case, theta is 1. Yeah. By definition, theta is 1. So I have this. So I have kx cubed. So this is, of course, larger than this. So so pi of star kx s squared, and this is beta and pi of star kx. See? So by definition, this is psi, beta psi, and beta is pg minus 2. So suppose you can verify that psi is larger than 4/3, then this is okay. Okay. So now I want to show you, in general. In general, this is possible, but in general, if GC is a genus 2 curve, it can happen that psi is 1. So you cannot use this, but you have to make use of this part. So I didn't write. Sorry, here I should add pi of star kx s e prime. Okay. So sometime we want to use this. So it's the first point is that it's when PG is when beta. Here we know that beta is at least 3 because PG is larger than 5. 5 minus 2, 3. So first, using the technique I explained yesterday, we can prove that anyway, psi is always larger than or equal to 1. To see that this is a Russian number. Usually this is a Russian number. So not, but if this is a Gorenstein case, so suppose you can prove that psi is strictly larger than 1, then psi should be at least 2. But in general case, this is since this is only a Russian number. So let me do a special case. So suppose the genus of C is at least 3. Then use my inequality tool yesterday. So we can see that psi is at least degree of Kc, and here is m0 is 1, theta is 1, plus 1 over beta. Beta is at least 3, so this is 3. So so here of course it's 3. So this is 4. Yeah. So this is 4 over 2 plus 1 over 3. So this is 12 over 7. Okay. Of course, this is already larger than 4 over 3. Yes. Yeah. So I think it's for my purpose, it's already okay. Yeah. This is 36. This is 28. Yeah. Anyway. Yeah. But in general, actually, we can optimize this. Yeah. Actually, we can do a couple of more steps. We can see that in this case, psi is at least 2. So we have kx cubed. This is more than 2 pg minus 4. So this this when this genus of C is at least 3. This is very good. So the difficult case is when GC is 2. What happens? Okay. So so when GC is 2, we have two cases. Either Xi is 1 or Xi is positive, strictly larger than 1. But in this case, this really happens. So this corresponds to Kobayashi's example. So obviously, we should make use of this term. We should estimate this term. Otherwise, you cannot prove this. So, but when Xi is positive, use my technique. We can see that. We can prove that Xi is still holds. So I omit this step because this is something similar to here. So the only difficulty is here. So this inequality only holds. This inequality holds for arbitrary minimum threefold, except GC is 2 and Xi is 1. So I will do this later. So I will explain this later. So this is the first case. Let me case 2. I left one case open here. Open here. So case 2. Case 2 is that a dimension of gamma equals to 1. So in this case, we have some more situations. For example, it's not hard to see in my papers, I have proved that this vibration, the induced vibration f x prime to gamma. So I assume that f is a fiber. It means a general fiber of f. So this is a smooth surface of general type. So there are only two types. So either Pg of f equals to 1 and g of gamma at least 2, or PGF. So this is, of course, this is positive, but G gamma is either 0 or 1. Okay, so we have only these two situations, but here we have a condition PG of x at least 5. So if PGX is smaller, then maybe there one more case, but this PG is at least 5. So we only two cases. So how can I do this? So I will do like this. So first, PG cannot be 0, PG of I fiber. So you just because F is a general fiber, so it cannot be in the fixed part of a canonical system. So then it's natural. So since a PG of X is positive, so the fiber should be the fiber should have positive geometriness. So this is simply because this you see this long exact sequence. So you have kx prime here, and you map this to kf. Okay, and the previous item is h not kx prime plus f. Okay, since f is a general fiber, it cannot be composed in the in the fixed part of kx prime. So this is a, this is a, this is, no. Yeah, of course. So this cannot be zero map. Okay. So PGF is positive. Yeah. PGF.
Why can't it be bigger than 1 if the unit of gamma is big?
Gamma is big. Yeah, this when G gamma is big, you mean why PGF should be 1? Now this because this is a canonically fibered case, so you just use some So you can calculate this by considering this by considering this shift f lower star omega x prime. Okay, you consider global section. The global section of this shift generates a subline bundle because this is a pencil. So you have so then you get you get a quotient here, and then you have H naught L naught. So this is isomorphic to H naught F lower star omega x prime to H naught L1. Yeah, and then using the semi-positivity. So you're using semi-positivity, that's F lower star omega x prime over gamma. So this is semi-positive. Then you can deduce this, but this is in my paper, so it's not hard to see. Yeah. So this is parallel to surface case. In surface case, G gamma either be 0 or 1. But in the surface case, this case cannot happen because a fiber is always genus at least 2. So the first case cannot happen. But in high dimensions, this definitely can happen. Yeah. So anyway, this is not the hard part. So I will consider this by some subcases. First, so I still write sigma to be f onto a minimal model. So first case, let me consider kf naught square is 2. So if you remember, yesterday I explained that Kawamata's extension theorem tells you that pi up star of kx, when you take the restriction onto f, so this is, of course, this is smaller than sigma up star kf naught, because this appears in the positive part of characteristic decomposition of this. So this is the biggest positive part in kf. Yeah. But this is never big, so of course smaller. But on the other hand, what we need is that this is at least theta. In this case, what is theta? Yeah. In this case, theta. Yeah, we have pi up star kx. This is theta f plus e prime. Here, theta is at least pgx minus 1. Okay, so theta, so when pgx, so this is at least 4. Okay, so then we have this inequality. This is theta over m naught is 1, so 1 over theta sigma up star kf naught. Okay, so this is at least 4 over 5 sigma up star kf naught. Okay, I want to prove that the slope is at least 4 over 3. So from this relation, we know that k cubed, k cubed. Yeah. So kx cubed is at least theta. Yeah, theta is pgx minus 1 times pi. Yeah, pi up star of kx square f. So suppose we can prove this is a larger than 1, or especially this is larger than 4/3, then we are done. But in this case, this is expectable because we have this is at least 4/5 sigma up star kf. Yeah, so roughly to see that pi up star kx over f. This is 16/25. Yeah, kf naught square. So suppose this is 2, then this is 32/25. But it's not enough. Yeah. So this is a very coarse usage of my inequality. But I don't want to use this directly. I still want to use my technique. I will take a moving part, a moving linear system on F, and using my key theorem to estimate this. So how can I do? So I see that since in our case PG is positive, PGF is positive, so 2 sigma. Yeah, I will do this using my setting. So take the base point linear system to be simply 2 sigma up star kf naught. This is base point free because nowadays it's well known that when PG is positive, 2k is base point free. So a general curve, a general member in this linear system is when in this case it's a non-hyperelliptic curve. Okay, so I take a general member C in this, and then what I want to do is to estimate this. So pi up star kx over f square. So this is pi up star kx over f. I want to produce C. What is C? C is here. So at least it's 4. Yeah, it's 2/5 C. That is 2/5 psi. So this is still the same. Yeah, still the same purpose. We want to estimate psi. So I repeatedly use my key theorem to estimate this psi. But I have to use one special property that C is is an even divisor, because this is C is an even divisor and non-hyperelliptic. So in this case, it's for me. I have no difficulty to get psi, and psi is very good. And anyway, so in this case, it's easy for me to prove that the inequality star still holds. Okay, so the left cases are kf naught square equals to 1. So let me. Yes? Yeah, strictly large. For my purpose, I want to prove that this is a strictly large for 4/3 PG minus 1. So in this case, so my result is this is, in this case is much bigger. Is much it's much better. It's nearly finally it's nearly 2 times PG minus 2. So this is a good, much better.
So then now if satisfy this equal, then only 2 cases.
Yes, there are only 2 cases. Yes. So the rest case is kf naught square equals to 1. So by Noether's inequality, we have 2 cases. First is PG of f equals to 1, and secondly, PG of f equal to 2. Okay. So in this case, this is a much challenging case, because you see that this can be, in this case this can be at least 1, at most 1. If this is a sigma, then it's a kf naught square, but this is 1. So the best you can expect, you can do is this, but this has nothing to do with our expected inequality. So we want to estimate this part. So this is also difficult. But one of these cases, for this case, I mean for the first case, for 1-1 surface, so we still can do this with another, by considering h naught 2kx prime onto to h naught 2kf. We know that P2. So this is a dimension. This is 3. Dimension is 3, but we have enough section here. So I just consider the image of this group. So the image, if the image is 3, then this is the 2k restrict to f is exactly the bicanonical map of f. But this is a degree 4 map. This is much better, And or the images of dimension 2 are dimension 1. So I use another method to prove this. And finally, in this case, we know that star holds. Okay. So I omit this case. So so this is very special. So let me do the left case, the 1, 2. Sorry.
Do you get exactly star, or do you get something slightly better?
Better, much better than star. So so essentially, the open cases is either we have a dimension of gamma equals to 1 and GC equals to 2 and psi equals to 1. Okay, sorry, this is 2. Okay, or this case, dimension of gamma equals to 1, but we have a fiber f is a 1-2 surface. So this have been challenging cases. So why can we do this in Gorenstein case? So yeah, in Gorenstein case, yeah, only until the last year. So for the case, let me say case A and case B. Okay, for case A, only until the last year we found that, so we can find a very special resolution of the of singularities. Yeah. So how can we do this for case A? So far, yeah, we assume that X is Gorenstein. And we have a moving linear system Kx n plus, say, sorry, I abuse of notation W. Yeah. So this is the moving part of Kx. So yeah. So very occasionally I found that Ronkai chain has been doing some has been constructing a very special resolution of singularity on threefolds. I found that in his paper actually, yeah, contained something. So I tried to ask him whether he can prove he can construct some special resolution of singularities or indeterminacy in a linear system and prove and control the discrepancy. So then after several tries, we found that it's okay. So the main problem is like this. So we want to, we construct, there exists some partial resolution. Say X double prime. So I still write this as as pi 2x. Here x prime, so satisfy the following conditions. So x double prime has isolated as terminal singularities. But this terminal singularity is non-essential. I mean, what do I mean non-spatial? Non-essential means that the moving part, so singularities are not contained. So this, or we say that the moving part of Kx double prime, so moving part of Kx double prime contains. So this is sorry. So this is base point free. This is base point free. But x prime can contain some singularities which are away from the. Yeah, the singularities are contained in spatial member of this linear system. So this is first, and secondly, what is pi? Pi is a composition of Kawamata blow-ups. So which is explained by Myers yesterday. So in this case, we want to control the discrepancy. So the key point is following lemma A. So in this setting, suppose we write kx double prime to be pi up star kx plus sigma. So this is ei. And on the other hand, we can write pi up star n. So here, let me write this to be m. So this is base point free. So we have this can be write m plus sigma ei prime ei. So by definition, we only do the blow-ups, and the center are contained in the base locus of this moving linear system. So all the exceptional divisors, appears in both in both sums. So the main result is that what we need is then we have we have for each ei is smaller than 2 ei prime. So this is what I need. Yes. Sorry. Yes, this is exactly what we need. So the point is that in a smooth case, if we blow up a smooth point, suppose x is a smooth threefold, and I have a linear system, moving linear system. When I blow up a smooth point, then in this discrepancy of the first equality, so this is 2, ei is 2. Okay. But on the other hand, this is at least 1. So this always holds. So in smooth case, if you blow up a smooth curve, the center is a smooth curve, then ei is 1. But on the in the second inequality, ei prime is also at least 1. So this always holds. But for a long time, I'm not sure. What I'm not sure is if x has some terminal singularities. But now, if x has Goran-Stein singularities, we can still have this. So this is this is what I need, exactly what I need. So suppose we have this for certain category of singularities, then our method for smooth case also works for general case. So simply due to this lemma, so we can generalize my original proof for this. So this is the first case. For the second case, so this is so far the most difficult case, but we can only assume that x is Goran-Stein. Sorry? Weighted blow up, yes. Yeah?
You don't mean canonical.
Yes. I mean, sorry, maybe I mean weighted blow up. Sorry. Yeah, I'm not sure whether. What? But no. Weighted, yeah. Even I begin with Goran-Stein point. When I take a weighted blow up, is the middle, in the immediate, in the middle cases we can get non-Goran-Stein, but finally we get Goran-Stein. So I don't know. Yeah, maybe this is a this is only a problem of notion. Yeah. condition, yeah, condition A, yeah, of course, condition A, not condition. This is not condition A. This is very general. Yeah. But the point is, here we need X to be Gorenstein. Okay. We need X to be Gorenstein. So I begin with a Gorenstein point, terminal point. And I do several.
You have a linear system on base, with base points.
Yes.
You're resolving the base flow.
Yes.
You never need to blow up a point.
I need.
It's a fixed point.
Yeah. First, I need to resolve this singular point in the base locus. Yeah. And then I. Yeah. Yeah.
Something which is index 1.
Um,
And after that, because you're doing weighted graphs, you might get higher index.
yes. So I blew up one point, even if this is Gorenstein, but maybe x1, x2, yeah, then finally xt. So in the middle part, it may happen that xi have a non-Gorenstein point, but finally I get Gorenstein xt here. So so this is not a very simple process. So excuse me, I can't explain more here due to my time. Yeah. So for last case, so X is Gorenstein. So what we can do is that with Catanese and Zhang, what we did is that we classify. Yeah, we classify canonical curve. Canonical curve C in KF naught. We want to control all the coefficients in this curve because this is a genus 2. Usually it's a genus 2 curve, but for special curves in this linear system can be some combinatorial complexity. But the point is that we classify all this kind of curve, and then using Fermat-Fivec theorem to prove that we have a P2 of X. So this is K minus 3 chi OX. And this is H naught of Kx prime plus pi up star Kx. Okay. See, on the left hand side, we're using Riemann-Roch. That is mentioned by Myers. And on the other hand, we can estimate the right hand side. So how can we do? So we try to we study we know that pi up star Kx is something like theta f plus e prime. So we have a lot of fiber here. So we restrict this f onto restrict this linear system onto some fibers to get first here what we get is that for any effective for any rational number t larger than 3/10, so we can see that h naught f kf plus t sigma up star any gamma. Sorry, canonical curve I should denote by gamma. So we know that this is 3, and then we use the Fermat-Fivec vanishing to estimate the right hand side. So how can we do? So simply So let me show you what we need. So h naught kx prime plus pi up star kx minus something, say yeah, M1 prime. Okay, so then we have Fi. This is some number T sigma up star gamma. Plus Kf. Okay, and so we have here, and this is 0. So we know that this is smaller than this. But if we can, so here we have some fiber nf here. So this is something like 3n. And here finally we estimate this part. This is something like so this is n1. So this is like 3n1, and this is like 2n1. So n2. Sorry. So n1 plus n2 is theta. So we estimate this, and then we get this is larger than something pg plus something. But this is in this case, chi ox is almost pg plus something. So so you get finally you get some inequality. Finally, the result is that kx cubed is 7/5 pgx minus 2. So this is what we get with Catanese and Zhang. But this is this inequality holds only for Gorenstein threefold. But in general, it's still open. So so finally, I would like to put one remark. So so far we don't have a counterexample to inequality star. So our hope is finally to prove this for any threefold, any minimal threefold. And recently, the advance is that for case A, we have solved this. For case A, we overcome this. So far the case B. The case B we are still doing on, but a couple of months ago we found that maybe this is true. So when we began to write, we found another gap. So I hope finally this will be a theorem. So this is I hope not very soon we can prove this. Okay, so this is what I want to explain. Okay, thank you.
Are there any questions?
Case A, so it's also solved without
So here, what I explain is Gorenstein.
But you can prove it also.
I can also prove with arbitrary, no non-Gorenstein, but this is not published yet. So it's
you use the same
yes.
more general.
We will get the same lemma for non-Gorenstein. Yeah. So, because this is a non-Gorenstein, so this divisor. So here we have more difficult because this is only rational numbers. So maybe some complexity. But anyway, we have written down this for non-Gorenstein. So for this case, this is still challenging for us.
Other questions? Okay, let's thank the speaker again.
Thank you.